Good afternoon, everyone, and welcome to our last Physics 112 recitation. I'm a little sad to see you all go. I definitely could use a break, and I'm sure you probably could as well. So the plan for today is we're going to introduce the thin lens equation, then we're going to talk a little bit about the final, and lastly we're going to do some review questions. So for the thin lens equation, we're going to start out by drawing that ray tracing that we had last week for the converging lens, or on Monday for the converging lens. So we have our optical axis, we have our lens, and we're going to draw in our key details. So we have our object here, we have our near focal point on this side, and then our far focal point is symmetric. So on the opposite side, the exact same distance away. And we're going to start drawing our lines. We're only going to draw two because we're going to do two different setups. We're going to make some right triangles, and we're going to use these to work out an equation that's going to give us a relationship between I, O, and F, where F is our focal length, I is our image distance, and O is our object distance. So the first thing we're going to do is we're going to draw the line that comes in parallel and then goes to the far focal point. Then we're going to draw our line that goes to the center. Now, if we were doing a full ray tracing question, we'd also want to draw our last line, which is the one that goes through the near focal point and then comes out parallel, because that's going to give us the intersection of all those lines is going to give us the location of our image. But the graph will get a little cluttered if we can't keep all of those in there. So I'm just going to draw the image in, and we're going to do a little bit of trig with some of the stuff. So this is where our image would end up being. Now, this is going to have an original height h. Since this is coming in parallel, we can draw a little light right triangle right here. This is also going to have a height h. This is going to have some angle theta. This is also going to be a right triangle. And since these two lines are coming together, this angle has to be the same as this angle. And this height is going to be some height h prime. This length here is going to be our focal length, because we're going from the center of our lens to our focal point. So this distance is f. For this here, well, our total length going from the center of the mirror to here would be our image distance I. So if we subtract off f, we're going to get this length here. So this length here is going to be I minus f. Now we're going to use the property of right triangles. So these are what are called similar triangles, meaning that the ratio of the sides have to be the same. So if you have a triangle that has all the same angles as another one, then they're called similar triangles, and the ratios of the sides are going to be the same. So what that means is if we take the ratio of h prime and h, that's going to be the same as the ratio of I minus f and f. We're going to have that h prime over h is equal to the corresponding sides then would be I minus f over f. So this is just using some trigonometry. And that's the first equation that we want to use. Now, we're going to redraw this in a second, and we're going to use another set of similar triangles to get another equation. But before I erase this, are there any questions to this point?
Yes, I have a question.
Yep.
What is I again?
I is your image distance, so going from the center of the lens to where the image ends up.
Thank you.
Any other questions? All right, so let's erase this real quick and redraw it. And this time we're going to put all three lines in. I'll do this one in this fuchsia color, so we have the two different equations in different colors. So we'll draw in our optical axis again. We'll draw in our lens. We'll draw in our ray and our focal lengths. And then we're going to draw our line that goes in parallel. and comes out through the far focal point. We'll draw our line that goes straight through the center of our lens. And then we're going to draw our line that goes through the near focal point, and then comes out parallel. And this is why you want to use a ruler when you're drawing your lines, because otherwise you may end up in situations where they don't actually line up like they should. Alright, so our image is going to end up roughly over here. And so we can make another set of similar triangles. So if we look at this big triangle right here, it's going to have some angle which we'll call theta. And it's going to have some height which we'll call h. And this length here, this is the distance from our object to our center of our lens, so that's our object distance O. Now, this angle here is going to be the same as this angle here. Because again, they're made by the same two lines, so that angle has to be the same. And we also have a right angle here and here, so the last angle has to be the same as well, and we have similar triangles once again. This is going to have a new height h prime, and this distance here, well, so this is this distance from the center of our lens to our image, so this is going to be our image distance I. So we can do the exact same game we did before. We're going to write out what h prime over h is. We're going to have h prime over h. Now this time we have this side is I and this side is O. So we're going to have h prime over h is equal to I over O. So are there any questions on this? Alright, so from here we're just going to do a little bit of algebra real quickly. And so I'm just going to take these two equations and set them equal to each other. So we're going to have I minus f over f is equal to I over O. We're going to multiply or just divide both sides by I to get rid of the I in this numerator here. And so when we do that, we're going to go ahead and get that 1 over O is equal to I minus f over IF. Now the tricky thing here, we're going to do a little bit of algebraic manipulation. So I'm going to tell you that this is the same thing as 1 over f minus 1 over I. And so we're going to walk through why that's the case. Well, if you want to find a common denominator for these, if we multiply this one by I, we'll get a denominator of IF, so it would have I over IF minus, this one would have to multiply by f, so it would have f over IF. And that would give you the same thing here. So I'm just going to take this and set it equal to that because they're the same thing. So we're going to have 1 over O is equal to 1 over f minus 1 over I. So now the last thing we need to do is get, we want to move the 1 over I term to the other side. So we're going to get 1 over f is equal to 1 over I plus 1 over O. And that's what's known as the thin lens equation. So are there any questions to this point? Alright, so the thin lens equation is going to be, we're going to find it's a lot more straightforward to use than ray tracing. So we're going to go ahead and do an example with it. So let's suppose that, I'm going to draw a little sketch for it, but if you can do this all in your head without drawing a picture, that's fine too, as long as Mr. Dudish doesn't say draw a picture. You don't have to have a picture there. You can just use the thin lens equation itself. But we're going to use a converging lens again. So I'm going to draw in our converging lens and our optical axis. Suppose that Cupcake is sitting 1 meter away from a lens, so that tells us our object distance is 1 meter. And so Cupcake is somewhere over here, and that distance is 1 meter. From a lens with a focal length of 0.10 meters. So F equals 0.10 meter. So our focal length is going to be pretty close to our lens on either side. What will the distance of the image produced be? Well, if we were doing ray tracing, we would have to go ahead and do all our lines, but since we're using the thin lens equation, we're just going to go ahead and take that. So we have 1 over F is equal to 1 over I minus 1 over O. Now I'm going to bring the 1 over O to the other, or that should be a plus, not a minus. We're going to bring the 1 over O to the other side, so we get 1 over I by itself. So we're going to have 1 over I is equal to 1 over F minus 1 over O. And so what I'm going to do is I'm just going to plug these numbers and reciprocate at the end. You could do a lot of algebra to get I by itself, but I find it generally faster just to plug the numbers in and take the reciprocal. So we're going to have 1 over 0.10 meters minus 1 over 1.0 meters. Now I'm going to go ahead and find a common denominator of 1, so I'm going to multiply this term by 10. So we're going to get 10 over 1 meter minus 1 over 1 meter is equal to 9 over 1 meter. Now we're not there yet because this is 1 over I and we need I itself, so we have to reciprocate. And so we're going to get that I is equal to 1 meter over 9, which would be 0.11 meters. So our image is going to end up somewhere over here, very close to that far focal point. Are there any questions on this example? Alright, so in this situation, our image distance turned out to be positive. And we say that if our image ends up on this side of our converging lens, it's said to be positive. If it ends up on this side, it's said to be negative. So under what conditions will I be positive or negative? And what about our focal length too? Can that be negative? So the next thing we're going to talk about is just briefly we're going to talk about when are I and F positive and negative. So our object distance O, we always define to be positive. But depending on the type of lens we have and depending on what situation we have, some of those other values could be positive or negative. And we're going to start with our friend the converging lens because that's what we've been working with up to this point. So for a converging lens, and for the converging lens, well, O we just said is always positive, so O will still be positive. F is also always positive, so O and F are positive. Now the tricky situation is I. So if our object is outside our focal length, so then I will be positive. If our object is instead inside that focal length, that's when it's going to be negative. So So anytime we have a converging lens and we're outside that focal length, our image distance is going to be on the opposite side of our lens and we're going to say that's positive. If we're inside that focal length, then it's going to appear on the same side as the object and we call that negative. Now we also have what's called a diverging lens. And the thing about a diverging lens is with our converging lens, our lines all converge to a point. With a diverging lens, what ends up happening is, so a diverging lens, we would draw something like this, usually to represent it. And so we have, if we put in our optical axis, we have some object, we have a focal length. What ends up happening is that our light rays actually diverge away. So we have one that goes like this. We have the one that goes to the center still is just normal. And that didn't really go to the center. But we're going to end up finding that our light rays, instead of converging to a point on this side, they're going to diverge, and it's going to be as though they came from a point on this side. So you have to kind of do that same backtracing thing we did with the virtual image. So for a diverging lens, it turns out that, well, O is still always going to be positive, but F and I are always negative. So are there any questions on this? And the textbook has a nice chart on, if you go into the section on the thin lens equation, so 18.7, there's a nice little box that it solidifies this information in a nice concise format. They also talk about mirrors, but we haven't had any videos on mirrors, so I'm assuming we're just working with lenses. So, and this would be the properties for lenses. Alright, so the next thing we're going to talk about, this is our last new concept, is magnification. So when you put an object in front of a lens and an image is produced, very rarely will that image be the exact same size as the original image. A lot of times it's going to be bigger or smaller. So how much bigger or smaller? Well, we can use the magnification equation to find out. So recall that when we were doing our trigonometry earlier, we came up with this relationship. H prime over H is equal to I over O. Well, if we were to multiply both sides by H, we would basically have an expression for our image height, because we said H was the height of our object and H prime was the height of our image. So we'll have H prime is equal to I over O times H. But remember that when we have our converging lens and the light goes through, our triangle ends up upside down. So if you want to take into account the fact that our height may be inverted, we're going to put a little negative sign in front of it. And so this part of our term right here is called the magnification, and we use an M to denote it. M is going to be equal to negative I over O. So it's that exact same relationship we had earlier, except in this case, we want to take into account that the fact that our triangle was inverted in some situation, so that's why we put the negative sign there. So are there any questions on this? All right, so let's move into an example. So let's suppose that we once again have Cupcake the kitten, and we have our converging lens again. So we'll start a little picture off to the side so we can kind of think about what's happening here. So we have our converging lens, and in this case, so let's suppose the Cupcake is sitting 0.050 meters from our converging lens. So O is equal to 0.050 meters. And the focal length is 0.25 meters, so F is equal to 0.25 meters. So Cupcake's actually going to be sitting inside our focal length. So if our focal length is like this and this, Cupcake's going to be somewhere in here. And so you want to know, and let's say, so Cupcake is 15 centimeters tall when sitting up. So that tells us that H is equal to 15 centimeters. And so we want to know first what type of image will be produced, and by that I mean real or virtual. And then we want to know how tall will the image be. So part A is what type of image. Well, if we think back to Monday's recitation, when we were inside that focal length, we ended up getting a virtual image that was somewhere off to the side here. So we're still going to get a virtual image. So anytime your object is inside the focal length for a converging lens, you're going to get a virtual image. So our image is virtual. Now to find the new height is a little bit tricky just because we know what O is, we don't have I, so going straight to the magnification equation isn't going to work. So we're going to have to use the thin lens equation first, and then we'll be able to use the magnification equation. So going to thin lens, we're going to have 1 over, and I'm just going to go ahead and solve it out for 1 over I directly, so just already move the 1 over O to the other side, so 1 over I is equal to 1 over F minus 1 over O. And we said our focal length was 0.25 meters, so we're going to have 1 over 0.25 meters minus, and then here we're going to have 1 over 0.05 meters. We're going to go ahead and find a common denominator. I'm just going to use 1 as a common denominator just because that's nice and easy. So we're going to have, this is going to be the same thing as 4 over 1 meter minus, and then this one is going to be the same thing as 20 over 1 meter. And so you can see that this is going to be negative this time around because this is bigger. And that makes sense if we think about it because we just said that the image distance should be negative if we're inside our focal length for a converging lens. So this is going to be negative 16 over, and then 1.0 meters. Now that's 1 over I. So if we want I itself, we just have to reciprocate. So I is equal to 1 meter divided by 16, which will be 0.0625, and we still have negative signs here and here. So we have that negative image distance. Now, are there any questions up to this point? All right, so now that we have our image distance, we can go ahead and use our magnification equation and figure out our new height. So we're going to have m is equal to negative I over O. Well, that's going to be negative of negative 0.0625 meters divided by our object distance was 0.050 meters, which will work out to be positive 1.25. So what this tells you is that our new height is going to be 2.25 times the original, and that our image is going to be upright. So if it had a negative sign, that's going to tell us it's flipped upside down over the axis, but this means it's going to be upright, which is consistent with what we know about virtual images so far. So to find the new height, we're just going to take our h prime is equal to m times h, so it's going to be 1.25. Now Cupcake's height was 15 centimeters. I'm going to go ahead and convert that to meters, so 1.5 meters. That's going to work out to be 0.1875 meters, or to 2 sig figs, 0.19 meters. So 19 centimeters. Are there any questions on this example? So that's the last of the new material I have for you today. So let's talk about the structure of the test. So the final exam is going to be next Thursday, not this tomorrow, but the Thursday after, so the Thursday of finals week at 8 a.m., so 8 to 10 a.m. And it's going to be on Blackboard. And it's going to be multiple choice, I believe. So Mr. Durish has said there's going to be probably about 20 multiple choice questions, so it'll be about 5 points each They're going to be computer graded, so there's not going to be any partial credit, which is unfortunate. Now the upside is the final cannot hurt you. So for those of you who did really well on the first 2 tests, even if you bomb the final, if you do worse on the final than you did on the first 2 tests, he will not count it toward your grade. However, those first 2 tests will then count double. So if you did maybe not so well on the first 2 tests, the final is a great time to bring up your grade a little bit, because it's going to count double if it helps you. So as long as that final helps you, it's going to count double, it's going to go into your grade. But if you don't do so well on the final, and you did pretty well on the first 2 tests, you'll be fine anyway, because it just won't go into your grade if it doesn't help you. And Mr. Douche has a thread on Blackboard, or one of the students started a thread on Blackboard asking questions about the finals. So he encourages you, if you have questions about it, to write them in the discussion thread so that everyone can see them and see what the answers are to those questions. But that's what little information I have about the final. Are there any questions on that? All right, if there are no questions about the final, we're going to move into a couple of review examples. So the first review topic we're going to talk about is the Doppler effect. And so let's suppose that you are standing by your window when a car comes peeling down the street at 30 meters per second. So the speed of our car is going to be 30 meters per second. And the car is blasting its radio. So our first part A, is going to be if the frequency of one of the notes is 200 hertz. So we have F equals 200 hertz from the car. So when the car is frame of reference, it's playing a frequency of 200 hertz. What frequency will you hear when the car is moving away from you? So car is moving away. We want to know what is the new frequency. What frequency will you hear? So for this, the first thing we have to determine, so remember that when we did the Doppler effect, we assumed that you were stationary, so we always had the stationary observer. But we had 2 different Doppler effect equations, one if the object was moving toward you, or one if it's moving away from you. So you have to figure out what's the right equation to use. Well, it says the car is moving away, so that means we're going to use the F sub minus equation, which if we think back to from earlier in the semester, it was equal to the frequency of our source divided by, and here we have 1 plus, so the only difference between the 2 equations was the F sub minus equation has a plus sign in it, whereas the F sub plus equation has a minus sign in it. So otherwise the equations look exactly the same. And we have the speed of our source divided by the speed of our wave. So from here, it's a matter of plugging in our different values. So the frequency is going to be 200 hertz. And then we're going to have 1 plus. Now the source is our car. So we're going to have 30 meters per second. And then the wave speed, well, it's a sound wave, so we're going to need to write the speed of sound. So it's going to be 343 meters per second. Now, I don't know whether or not Mr. Douche will be giving you the speed of sound on the final. It may be one of those constants that you have to know. So I would recommend, making yourself a help sheet for the final with all the relevant equations and constants. So since the test is happening online, I'm not sure whether he intends for it to be open notes or not, but I have a feeling that it's probably going to become an open notes thing. However, it's much easier to flip through a couple pages of a help sheet rather than a whole binder of notes or a whole textbook. So just to prepare yourself for the final, I'd recommend writing out your help sheet like normal, making sure you have the relevant equations on there and any of that sort of stuff. So we have our speed of sound, which is about 343 meters per second in air. And so if we crunch our numbers, we're going to get that F sub minus is equal to 183.9 hertz, or to 2 sig figs, 180 hertz. So are there any questions on part A of this question? Alright, so something else we might want to know about our wave is, what is the wavelength for you? What wavelength do you perceive? So part B, we want to know what is lambda minus. Well, we'll think back and recall that our wavelength is equal to our wave speed divided by our frequency. So here, our wave speed, well, this is sound that's traveling, so we're going to have the speed of sound, so 343 meters per second. And then that frequency is the new frequency we just found, because we're talking about lambda minus, and so that goes with F minus. And so that's going to be 183.9 hertz. So if we plug this into our calculator, we're going to get that our wavelength is about 187 meters, or not 100, 1.87 meters, or to 2 sig figs, 1.9 meters. So are there any questions on this example? Alright, so for our last equation, or our last review topic, we're going to head on over to beats. And we're going to do a graphical question, because we know that Mr. Dudish loves graphs. And so you won't be expected to draw a graph on the final, which is nice, but you may very well have to identify key parts of a graph. You may have to answer questions about graphs. So we're going to do a beats question involving a graph. And this should look fairly similar to a homework question we did that was a bit tricky for us and we had some trouble with. So I'm going to draw this to the best of my abilities. My drawing skills, unfortunately, for drawing nicely spaced waves on a whiteboard are a little lacking, so we'll do the best we can though. So these are going to be sound waves, so our amplitude is going to be the change of pressure, and then we're going to have time in seconds on this axis. I'm going to try drawing the envelope of the wave first. And this should, in theory, be all nice and symmetric, but it's the best I can do at the moment. And so now we're going to draw our individual little waves in here. We have this one goes up, down, up, down, up, down. Oops. And in theory, these should all be nice and evenly spaced, but this is as close as we can get. So this is what our graph looks like. So we have the envelope of the wave in green, and then we have our little oscillations in purple. That's the actual pattern you get from the overlap of two waves. So they have two different frequencies, F1 and F2. And when you add them, this is the pattern they add to. And so we're going to have several questions on this. And before we get to our questions, let's put some units on our axis. So this right here is 1, this is 2, this is 3. So our first question is, what is the beat frequency? So part A. So what is that beat frequency? Now recall that one beat is one soft, loud, soft pattern, or one loud, soft, loud pattern. So if we look at this, we have 1, 2, 3 soft, loud, soft patterns. So that means we have 3 cycles. And how long does it take? Well, it takes 3 seconds to get these 3 cycles. So we have 3 cycles in 3 seconds. That means our beat frequency, F beat, is equal to 3 cycles per 3 seconds. Which will work out to be 1 hertz. So our beat frequency is 1 hertz. So are there any questions on part A? Oops. So for part B, the next thing we want to know is what is our oscillatory frequency? Well, to do this, we have to count how many cycles there are of the purple lines. And so there's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Roughly 12 cycles in here. So that means we're going to have 12 cycles in 3 seconds. Which is going to work out to be 4 hertz. So are there any questions on this part? Alright, so we know that this pattern is created by the interference of 2 very close waves with frequencies F1 and F2. And so our last thing is we want to know what is F1 and what is F2. That's our final goal. So what are F1 and F2? To answer this question, let's recall what our equations are for the oscillatory frequency and the beat frequency. So we have FOSC is equal to 1/2 F1 plus F2. And then we all have that our beat frequency is equal to F beat is F2 minus F1, the absolute value of that. Now we want to drop the absolute value sign, so I'm going to assume that F2 is greater than F1. And the reason why we can do that is that F1 and F2 are just labels. It doesn't matter which wave we call F1 and which one we call F2, or which frequency we call F1 and which frequency we call F2. They're just labels. So I can say that this is the bigger one, and that's okay. And then we can just drop the absolute value sign. So we're going to have F beat is equal to F2 minus F1. Now I'm going to take this equation right here, and I'm going to multiply both sides by 2. And the reason why I'm going to do this is I want to cancel out one of our frequency terms, and since these are halved, that's going to be a little tricky, but if I double it, then we can do that. So I'm going to take this and multiply it by 2. And so we're going to get 2 F oscillatory is equal to, the 1/2 is going to go away, so we're going to have F, and I'm just going to rewrite it so it's F2 plus F1. It doesn't matter which one comes first, just so that our F2s and F1s line up over here. So now let's add these two equations together. And so we're going to get that F beat plus 2 F oscillatory is equal to, well, here we're going to get 2f2. But the f1s are going to cancel out, so we're going to be left with this expression here. So our next step, we're going to go ahead and plug in our values for f beat and f oscillatory that we derived earlier in parts A and B. So we're going to have 2f2 is equal to, well, we said our beat frequency is 1 hertz, so 1 hertz plus our oscillatory frequency is 4 hertz, so 2 times 4 hertz. And that's going to be equal to 9 hertz. So 2f2 is equal to 9 hertz, so f2 would just divide by 2. So f2 is going to be equal to 9 hertz over 2, or 4.5 hertz. So from here, we need to find f1 still. I'm going to use this equation right here, and I'm just going to plug in the 1 hertz for f beat because we found that earlier. So we're going to have 1 hertz is equal to f2 minus f1. I'm going to move the f1 to the other side and the 1 hertz to the other side. So we're going to have f1 is equal to f2 minus 1 hertz. And then let's substitute in what f2 is now. So this is going to be 4.5 hertz minus 1 hertz. So we're going to be left with f1 is equal to 3.5 hertz. So are there any questions on this example? Are there any questions on anything we've covered at all during the semester? Well, during this part of the semester since we came back from spring break, since the test is only going to be on what happened after spring break. Alright, well, if you have no questions, that is all I have prepared for you for today. It's been great working with you, so thank you once again for a great semester, and good luck with finals, and have a great summer.